Okay, it should be recorded right now. I share my screen. This one. Okay. So this is the model that we are looking at for Wednesday section. We are done with tensile, and I still have a couple of students who haven't submitted their report. I'm waiting on them. I'm gonna grade them all before the midterm. I haven't decided on the midterm yet, but it's not a problem. So you shouldn't worry about your grade if you submit your report for it. And the torsion experiment. Let's go to concrete first, because there were a couple of questions on the concrete. They were asking about the due date of the concrete. So we are still waiting on the 28-day data because we haven't tested the other specimen. We only test our first cylinder, 7 days, which was last week. So if you watch the videos on concrete, and if you already start your reports on theory sections and the procedure sections, you should be okay. And you should already be able to calculate the required sections on the Excel spreadsheet. Let's look at this Excel spreadsheet. Okay. I forgot the slump on the first class. I believe it was 2.75 or 3 inches. So you should look at your notes, and then you should include the slump. You should calculate the cross-sectional area by now before you start the calculation of the 7 days table. You have your deformation that's given for 7 days with the corresponding values on the applied load. And the stress calculation is simple. It is basically the applied load divided by the cross-sectional area. So once you calculate your cross-sectional area, you're going to be able to calculate these sections easily. And for cross-sectional area, I know it is pi over d squared over 4, pi times d squared over 4. So pi is 3.14 times diameter is 6. Over 4. Okay. So I got my cross-sectional area. Now I got the values in PSI. I can clear it up a little bit. I want to see 2 decimals, or I can make it 1 decimal. If you can mute your speaker, your microphone, that's perfect. Anyway, and the strain values, same as we did before. You have your deformation divided by the gauge length, 12 inch. And then you're going to do your own graph. So in less than 2 minutes, I tabulated all the values, I calculated, and now I have to select the data for my X values, for Y values, for 7 days. And then once you get your 28 days, you're going to have one more plot, and it will be superimposed to one superimposed to the 7-day plot. And you have your expected results. Like I said, we are expecting to have 4,000 PSI at the end of 28 days, which was advertised on the quick concrete mix. And for 7 days, I was expecting 2,800 PSI, and we got 2,200 PSI. So that's it for the concrete. So once you get these data, load and deformation, you should be able to develop your graph, and you have the sample on the Moodle. But you still have time for this. Now we can look at the torsion. So the only reason I didn't do the torsion because I already had found a virtual simulation, and we're gonna go to virtual simulation step by step. I will explain what you were supposed to do and what you were supposed to submit. You have your PowerPoint. You should have started from PowerPoint first, then go to the virtual lab assignment. So this PowerPoint basically was developed for you to understand the like what type of equipment we are using for this type of experiment. In previous classes, I walked you guys through the equipment that we use for torsion experiment. See, again, it's Tunis Olsen torsion tester. And if you have done the virtual lab simulation, you know why do you need to use the micrometer to measure the diameter of the specimen. And then we tested 2 different specimens, aluminum and steel. And the second slide was the properties of the tested specimen. So you can look at the properties of 2 different specimens that are tested, and you can see the tensile strength, you can see the yield strength, and elongation, etc. These are the theoretical values, and you can see the typical uses of these type of materials. Theory was given to you. You just need to summarize to do your report. Again, report was not mandatory. I didn't. I mentioned in the email, but I didn't say that the report was required for this lab, or it wasn't due today. So I'm going to assign this torsion report today, and it's going to be due next week on Wednesday, and we will get to that.
The fact that I couldn't find that crap anywhere.
So, can you please mute? Guys, give me 1 second. Let me mute everybody. I believe it's good time.
So then, do you mind if I ask just a quick question about like the virtual assignment and all that?
Yeah, but I will get to the virtual assignment, but go ahead, ask your question.
Oh, I was just gonna say, like, I already did like the questions like for the assignment, but I noticed when I was trying to like upload it to Moodle because I saw it was due today, the Turnitin wouldn't let me actually like turn in the PDF file of this. So that was the only thing I just wanted to tell you.
Well, I'm gonna change the due date so you can fix it if you're not able to upload. That's not a big deal.
Cool.
The idea is you're trying to learn what is torsion. Okay, so the theory section you should include on your report next week, and the torsion theory, you can watch these videos. It's just 5-minute short video. And the experiment, since I didn't make a video in our lab, and this is the same equipment that you saw at the first slide, and it's a 20-minute video. You can watch every single steps and see what is the procedure they are following and how they are measuring the data. And
I have a question.
Wait.
The PowerPoint, when I pressed it, I couldn't watch the videos. Are they, the second one you showed was obviously a video I watched through the links. Are they all in the links in Moodle? Like the first one I couldn't see.
Yes, they should be in the section, torsion section, torsion
The first one is not. I had to look for it myself through YouTube to try and find it.
This one?
No, the one with the digital graphics.
Wait, for the torsion, we're only supposed to do the assignment and the quiz, right? Or we're supposed to turn in a lab report next?
No, lab report was not required for this week.
Okay.
You had quiz, and then you had the assignment, which I didn't get to that part.
Right.
Then let me finish my part. Let me
Okay.
explain, then I'll get to the questions. Okay.
Perfect.
So if you were not able to watch this video on the PowerPoint, then I will add this link. This link. Oh, it's not linked.
Yeah, that one there. That's the one we couldn't access.
Okay, I'm able to access, but I will fix it. I will fix
Thank
it.
you.
Mm-hmm. Okay.
By the way, if you just search up the name of the lab on YouTube, that video is going to be like the third video.
If I do what?
If you search up the Torsion lab on YouTube, this video that you have the link for is going to be like the third video.
Okay, thank you. Thank you. So if you search torsion on the YouTube, like you heard, it's going to be the third video. Anyway, so after you watch these couple of videos and look at the theory sections, as well as the spreadsheet that is available on the Moodle, you should be able to calculate these sections. And step by step, I explain how you need to calculate the given, required sections. You need to calculate the radian column. You need to calculate the rate of twist. You should, in order to calculate the radians, you're going to use the degrees. You're going to convert from degrees to radians, and the conversion unit is given here, 57.29. Once you calculate this, you will calculate the rate of twist, which is similar to the strain. It is a deformation per unit length. If you look at the equation, it is gamma divided by the original length. It's going to be, the unit will be radian per inch. And then you need to calculate the maximum strain in radians. This is the equation. C is the distance from the center of the tested material to the outer diameter. In other words, we are using the radius. You can replace C with the radius. Diameter is 0.75 and radius is 3.75. Divided by the gauge length will give you the maximum strain. Then you're going to calculate the maximum stress using this equation, TC, torque, this value, multiplied by the radius, C, divided by polar moment of inertia. And this is the equation for you to calculate the polar moment of inertia. And I can do some sample calculation on the spreadsheet that is on Moodle right here. Torsion test previous experiments. I will get to that. And you should calculate the shear modulus using the equation below. G is the shear modulus, and again, it only applies in the linear elastic portion. When I say linear elastic portion, this portion right here, it's up to 5,000 inch-pounds torque. You should have your shear stress and strain graph, and you should have one more graph that's showing the only elastic region. But like I said, you can calculate the modulus of elasticity or shear modulus in this case, or in regards to torsion. The slope of this line, linear line, will give you the shear modulus. You can either use this equation, G shear modulus divided equals to shear stress divided by the shear strain, change in shear stress divided by the change in shear strain. It's also the slope of this line. So if you calculate the slope of this line, you can get it from the spreadsheet, Excel. It tells you what the slope in this line. You can use either or. Requirements, you need to summarize the theory, summarize the procedure. You need to tabulate the maximum stress strain results for both specimen, these two tables. And then you should include your torque versus angle of twist graph, shear stress versus shear strain graph, and one more additional graph. This one shows a graph that shows the elastic region only. And you need to use this graph to determine the shear modulus. And you're going to have your discussion and conclusion part. Discussion and conclusion part, you can include the assignment questions that you answer on the virtual lab, basically.
I thought we weren't doing a lab for this one.
Like I said, last week, I only assigned 2 homework. One of them was the assignment on the virtual lab. The other one was the quiz, that quiz. For this one, I want you to prepare your report. Why? It's too much work, Andrea?
No, it's just you've said time and time again that there wasn't going to be a report, and now you're telling us that there is a report, so I'm just confused. What do you expect of us?
What I'm trying to say is there was no report due because I didn't cover this lecture on Zoom meeting. So I didn't give you these details, and I knew that some of you guys were going to be confused. That's why I waited for me to explain in details so you can start your report and you can finish it without having questions. Now, I believe that all the questions are clear and you can use this data to submit the report. Okay? So you can, this says extra credit, right? So if you did this quiz, extra credit, 2 problems, you're gonna have extra 30 points goes on top of your grade, right? If you haven't done it, then that's okay. You're not gonna get your extra credit. Whatever is the grade on your report, it's gonna stay in your report. So I'm trying to give you guys extra credit. But if it's too much work for you, then that's okay. You don't have to do the extra credit. You're not gonna get additional points on your report. Okay? You're still confused? If you're confused, I'm gonna keep on continue, answer your question. Ask me, why are you confused?
If we do the extra credit, would you want us to email it to you, or do you want us to submit it on the Turnitin?
Well, there were 2 Turnitin assignments. There is one assignment for virtual lab. There is one Torsion quiz submission, which was this quiz, right? And
So you're calling it a quiz on Moodle, but it's technically the extra credit that you've put at the end of the PowerPoint.
Right.
Thank you.
No problem. No problem. I'm trying to make it work. I'm trying to give you guys extra credit so we don't deal with problems when it comes to midterm and final. So I can use these extra credits to bump up your grades because I have to have proof.
So just for clarification and consistency, can you put down that it's actually the extra credit and not a quiz for the Turnitin, please?
So right here.
On Moodle.
Yeah, so it's not the virtual assignment quiz, it's the extra credit that we gotta turn in?
Yes, extra credit. I just fix it right here. Torsion quiz submission, extra credit. And let me make it clear. 30 points.
I have a question.
Thank you.
If you had 70, let's say you got 70 on your torsion, right? If you get 70, and if you solve these 2 problems, and if you get a correct answer, then it's going to be 100. Your report is going to go 30 points higher. 70 will be 100. 60 will be 90. Make sense?
I have a question on the virtual lab.
Mhm.
So for the quiz that we take on the virtual lab, does that just automatically go to your like grading book or
No,
something? Or we have to show you what our grade is?
Okay, let's go to virtual lab. There was one quiz and one assignment, and only the assignment, 4 questions or 5 questions, is assignment. This was the assignment, and you should have answered 5 questions and submitted in PDF format. That's it. That quiz, that was for you to solve, because I cannot save this quiz and you cannot save the answer. You can just check your answer if it's right or wrong. Is that the answer for your question?
So basically that quiz doesn't count?
That quiz doesn't count.
It's the assignment, bro.
Huh? What is it?
It's this, like, I was gonna answer his question, be like, it's just the assignment. He wants you to turn it in those 5 questions where it says assignment. That's what he wants.
Exactly. I want only these 5 questions. And I believe okay, maybe I didn't make it clear right here. And I say this is a great torsion experiment.
The thing that made it very confusing is that you had torsion quiz submission and there's a quiz in this virtual lab, and that's where the confusion came in. So clarifying that it's the extra credit 30 points from the PowerPoint helps. Now there shouldn't be any more confusion.
Perfect. As long as we're on the same page, that's the goal. That's why I mentioned before the class in the email, I want to clarify things. And then I also mentioned that I'm going to give extension on the quizzes, on the quiz, the extra credit quiz, and the virtual lab assignment. So even if we haven't done it, you can still turn it in. Or if you're not confident on your quiz or on your assignment, you can still work on it and then submit it by next week. And if you're confused about the torsion, I can have one-to-one section, Zoom section. We can arrange it, and I'll help you step by step, however you wanna proceed. So, any
I was
more?
gonna ask one last question.
Okay, go ahead.
We do not have 2 lab reports due next week, or we do?
No, you do not have 2 lab report due next week. You're gonna have only torsion lab report next week. I'm gonna cover the part of buckling today, buckling theory. And then I'm gonna do the experiments for buckling, upload the data on Moodle. Then you're gonna have the buckling report due. So for next week, only torsion. Okay?
Thank you.
No problem. Is it clear, Piero? Did you understand? Piero?
Yeah, we just have the torsion for, we just have the torsion report due next week. That's it.
Yes.
And then if you did the report, or if you did the 5 questions, that was the first link. His extra credit is the quiz that he's talking about in the Moodle. That seems about accurate.
Yeah. Yeah.
Sounds good. Sounds perfect.
Yeah. It's gonna be extra paperwork for me to grade, or for my assistant to grade. Like this quiz and the assignment, it's gonna be extra work. But I want you to get extra credit so you can bump up your grade, even if you get low score on your reports. So it's not actually a win-win scenario. I'm losing, you're winning, right?
I have a question based on what I had emailed you about the virtual lab.
Okay. Go ahead.
If you bring up the virtual lab and look at the theory, I'm curious to know if yours is wingdings or if yours is actual, like, pieces that you can read.
Okay, this.
Yes, that it's all wingdings. I was having a lot of trouble just trying to understand what it was saying, because that was the first thing I looked at.
I see. I see. I see. I don't know why it's doing that. It wasn't doing when I assigned this. I went through. Now this
Yeah,
part,
it was giving me trouble as well.
got you. Well, this section, it's just explaining the equations, derivation of the equation that we use. For example, this is for shear strain, how to calculate the shear strain using the radius r right here. This is the radius r multiplied by the deformation divided by the original length. And I can show you this equation on the spreadsheet right here. This equation, shear strain, radius multiplied by the radians divided by the gauge length. So if you cannot read this section, these sections, you can just go to the PowerPoint, or you can go to other files that are on Moodle, and you can replace these sections. Okay, if that's the problem. I'm not asking for you to derive the equation. This is more in details. These are just a derivation of the equations, and you don't need it. All you need to know, these equations, torque is equal to shear modulus multiplied by the radians divided by the gauge length, and multiplied by the polynomial of inertia. So if you know shear modulus, if you know the deformation and the gauge length, and if you know the polynomial of inertia, you can calculate the torque. Or if you don't know the shear modulus, if you know the other parameters, you can calculate the shear modulus. This is the only equation that you need to know. This is just a derivation, and you should know this derivation on your mechanics of materials class. And I don't have to go through the derivations because it's more time consuming. I understand your frustration. You were not able to read it, and I saw your email, but it was complicated for me to respond. On that time, I wasn't on my laptop, and then I forgot. But now I'm giving you I'm explaining this situation, how you can fix it. Instead of looking at this theory, you can just go to PowerPoint, or you can go to any other files, like these videos or the experiment sample data and result section. It will help you to clarify the equations. More clear, Andrea? Hello?
Yes, sorry.
Okay, yeah. Sorry about that problem, but it's a technical problem that I cannot fix it on my end. But other than that, the rest was clear, huh? Okay, you look at the theory sections and the procedure, and pretty much the same step that I explained how you measure the diameter with the micrometer. The simulation section, you can actually start the experiment and take your measurements.
My other problem.
What is the other problem?
My other problem with the virtual simulator is that the equations on the last part were not formatted correctly. And so instead of d to the fourth, it looks like you have d times 4. So there's a lot of things with this simulation that aren't formatted very clearly.
I wish this simulation was from UNO, but I found this online, and I did my best to do the research and come up with the simulation, because we were not able to perform the experiment.
Yes, same.
So
I got the percent errors really wrong. Do you want us to mention those in the lab report, and also mention that the simulator was a bit confusing and that we kind of mixed up the equations because of it?
Why don't we do this? Why don't we do this? So you did the simulation, you learned the procedure, and you learn how to measure the data. So by now, So far, you are able to follow the procedure, take these initial measurements to fill up your table. When I say the table, this table, right? These are the values that you need to determine, like diameter, and calculate the cross-sectional area, measure the length, and then start the experiment, measure the deformation in degrees, and then measure the corresponding torque. You are okay up to this part. Simulation explain you how to perform the experiment. Are we good, Mimi? Okay, so why don't we use this data instead of the data that's provided by the simulation? Would it be more clear for everyone?
Yeah, it'd be a lot more clear because it was like 4 calculations we got. It wasn't like all that data.
Mm-hmm. But if you look at from bright side, you spent good enough time to understand the subject, understand the theory. And what is the goal? What did I say at the beginning? The goal is not to pass this class with an A, just to learn the logic behind it. So you already excel the procedure and you know what you are expecting to have at the end of this experiment. And this is what you got. And if you follow this procedure, if you calculate the required sections, and if your graphs are similar to these, and I believe these graphs are made, I made these graphs based on this data. So if your graphs are similar, then you're on the right path. So you use these 2 data. You have that aluminum results, data for aluminum, and you have the results from steel. Okay?
Hey, Professor.
Yes.
I might have just done it wrong. So for the Excel file that you provided, where it has the aluminum data, steel data, and then you have aluminum and steel part 2. For the first part, the tables were empty, so I just kind of assumed you were giving us the data in those, and I just like completed those tables. So I'm guessing that was incorrect, and you wanted us to use the simulation data, or could I just use what I did already?
Okay. So like I said, we are not going to use the simulation data. This is the torsion test previous experiments that I downloaded from the Moodle, this spreadsheet. And you should use this spreadsheet to develop your tables and then generate your graph. Okay. Like here, you have your theory. You have all the theory that I explained when I put it on the PowerPoint. It's right here. And you can just summarize it and the aluminum data, these data sections.
Yeah, that's what I use.
Let me see if they are the same, starting from 280, 53. Yeah, they are the same. So let's look at this. So even when you look at this table, your first graph that was required, it's already generated automatically. Like Andrea, if you look at this spreadsheet, the first graph is already generated because I already selected data sections for X and Y components, X and Y axis. And next, I have to calculate the radians using this equation. So if the deformation is in degrees 1 degree, and if 1 radian is 57.29 degrees, select this 1 degree divided by 57. I got the deformation in radians. Next, rate of twist, deformation divided by the gauge length. So I select this cell, deformation in radians, I'm dividing it by the gauge length, 6 inch.
Shut up, bitch.
Okay, maximum strain.
I'll make you
This was the radius. I have to calculate the radius here first. Equation is not given here, but equation, if you want to look at the equation, it should be here somewhere. If not, it is here. I'm looking at this equation. Okay. From this calculation, I have to know the radius C. If I know the diameter, divide by 2, I got the radius 0.375. Then plug into the equation, radius.
When you're done with this one, can you show us the rate of twist calculation again?
Mm-hmm.
Thank you.
Sure. Something is not right.
The cell needs to be locked.
Mm-hmm. Thank you. See, you study your lesson. Good. Cell needs to be locked. B7. And then maximum shear stress. That was the torque applied multiplied by the radius multiplied by AC divided by J. Sorry, the J. I don't know the J value. Let's see what is J. Hold the moment of inertia. It was pi d squared, pi d to the 4 divided by the area. Let's see what is the equation. Can't think. Right here. So I have my equation. Pi over 2, 3.14 times c to the 4th radius to the 4th divided by 0.03. That's it. They are in KSI. Check the units. So I just did it in front of you guys, so I don't know if the numbers are.
Can you show the rate of twist equation again, please?
So you would have to divide that by 1,000 to keep it on KSI, correct?
Right now,
On
everything is in PSI.
Everything's on PSI right there.
Let's put everything on PSI then.
Okay.
So just check the units after you do your own calculation. So rate of twist is calculation.
Yeah.
It is the radian deformation in radians divided by the gauge length. Radian divided by the gauge length. It's one equation.
Thank you.
And then those radians, where'd you pull the radians from? Like, what's the equation for it?
This is the conversion.
So,
One radian is 57.39.
okay, so you just convert it. That's it. Okay, cool.
Starting.
Yeah. I mean, graph looks fine to me. Guess
Can you
what?
show us how you create your graphs? Because for some reason, I always struggle with creating graphs on Excel.
Well, did you take the graphic course? I mean, just asking, you know.
Yeah, I did, but every time I have to copy and move it over to a different cell, then that way I create my graph. But I've seen you just create your graph while it's in the actual chart.
I have not taken the graphics class yet, so I'd like to see this too.
Perfect. Okay. So let's start with this one. This is shear stress versus shear strain. Right, this graph. First, when I right click, do you guys see these color sections, highlighted colors? One for the shear strain, the other one for the maximum shear stress. Okay. Select data, and I'm gonna remove it. Now I have nothing. Or you want to start from scratch? Let's
might as well do scratch.
Insert. You're gonna go to insert. You're gonna go to chart type. You can select scatter with smooth lines and markers. So once you click it, it should appear here somewhere. Let's do it one more time.
I think it's because you have that graph selected. That's why it's doing that.
Okay, yeah, it's doing creating multiple graphs. Okay, so I start from the scratch. I got my blank graph. Now I have to select the data. I'm gonna add the series. I'm gonna select the series name 1. Just say 1. And the x values. That x values is gonna go to the x component, x-axis, right? Which is the horizontal axis. What do I want to see on the horizontal axis? I want to see the shear strain, right? Starting from 0. And then on the y-axis, I want to see the shear stress, maximum shear stress.
Is it going to give you an error since you have selected also the question mark?
Yes. Thank you for telling me. I was gonna say it's not gonna start from 0, right? So I didn't want to go back and fix it, and I can just fix it right now, and it will fix it automatically. Okay, we're not done yet. Looks quite similar to what we have right here. Right or wrong? Identical?
Yes.
Okay, Andrea, tell me which portion is the elastic portion, linear portion? Which portion is the elastic region?
Elastic region is the part that goes up until the curve. I can't see the numbers very well from here, I'm sorry.
Okay, 1 second. Jesus. I don't know why it's doing that. Okay. Okay, so intuitively you can say that this elastic region ends somewhere around here, right? Because it's
Yes.
leaving the linear portion, it's leaving the first degree plot, and it's going to second degree plot right here. You see the slope is changing right here, and then you have the plateau. Perfect. So second thing, you already exiled the theory and procedure, and you learn that you can only calculate your shear modulus from this region, right? And I mentioned that you can use the equation, a similar procedure, similar logic that we have on the tensile. The shear modulus is equal to the slope of this linear portion, the elastic region, right? It tells you the resistance to deformation, how strong, how durable is my material against the deformation. In other words, how much stress it's required to deform it permanently, right? So I know in this region it's only deforming elastically, and I can calculate this shear modulus from this region. If I want to get the slope from this graph, it's going to give me a goofy number. I need to develop another graph in details to get the slope of this linear portion, which I will do in a second. So you have no question mark in your head when you're doing the same things. Because basically I'm solving this, I am giving you the answer for your level course. This is the same data that you're gonna use. Okay, let's continue. Table is not over. I need to add the title. Title is maximum. This is for aluminum. Aluminum specimen. Maximum shear stress versus maximum shear strain. Perfect. What else? I don't know what these numbers are for. 1.5, 0.1, 0.5, 1, or 25,000 psi, 25,000 or 30,000. I don't know what they're standing for. So I have to label. I have to create the label. So you go to here. You have your axis. You have your axis titles. This is going to be the maximum strain, and the unit is in radians. And then I will have my y-axis, my vertical axis. It represents the maximum shear stress. Okay. Now I included all the data points, starting from 0 to 400, 4,500, yeah, close to 4,400 psi, right here. What else is missing? I believe we have everything for this graph. I know when I look at this graph, which axis is representing what. So any question on how to develop this graph? Who asked me the question at first place?
I did. Now I get it. Thank you.
You get it? Okay, perfect. So you got this one. Same thing. Then you already have this graph automatically will get generated. And even these graphs will be generated if you use the same template, same Excel spreadsheet that I provided on Moodle. This one. Once you calculate the data, you should be able to see these graphs already ready for you. So I was mentioning this, the linear portion and the shear modulus. I don't know why they're so small, but I can change it. Now it's more clear.
And just to confirm, we're using the same numbers in the PowerPoint, right?
Yes, you are using the same numbers from PowerPoint, and those numbers are already in this spreadsheet. Even if they are not in on your spreadsheet, you can just plug in the numbers from the PowerPoint and you can do it. So these numbers, those are the numbers that I'm working with right now. The aluminum numbers, 280, 520, 730, so on and so forth.
And that detailed graph that you were just showing, that's the same exact graph. That's just literally the detail of it defining the slope.
Yeah, 1363.9, this is the slope. This is your shear modulus. This
That was
one.
pretty good.
So this one is including only linear portion, maximum shear stress in PSI. Change the units. Even I mess up on the units sometimes. I don't pay attention, but it's important. There is a huge difference between 1000 PSI and 100 PSI and 1000 PSI. So make sure you pay attention to units. To do this graph, this thing, you can get it from the graph. Jesus. You can go to trend line. Where was it? More options. Display an equation on the chart. So if I right click and if I select the trend line options, I'm gonna do it again. I'm on the detailed version of the graph. I'm gonna right click right here or go to trend line, more options. On the right side, I can go down, I can display the equation on the chart. This equation is the equation of this line. So whatever the X number you enter, let's say the X number right here is 0.0163, it's gonna give you the Y number, right? And if you go back to your linear algebra, your algebra course, what is the equation of the line, linear line? Y equals mx plus b. And m is the slope, x is the parameter that you plug into your equation, and b is the constant number from the equation. And y will be the resultant. Any question on how to calculate the shear modulus and develop this graph? Okay.
Shear modulus was which one again? I'm sorry, I had to answer the door.
So the shear modulus, you're going to calculate it from the detailed graph. And you can also have another column right here for shear modulus. And you can enter, let's say, shear modulus like we did on the tensile. And you can enter the equation from the PowerPoint. This equation, shear modulus applied only in the linear elastic portion. Change in the shear stress divided by change in the shear strain. So what is the change in the shear stress? This minus this. I'm sorry, this minus shear stress divided by the shear strain. I'm not including the changes because when you subtract 0 from 3381, that's going to give you the same number. So I skip that change and I go down. I'm going to look at these numbers closely. And they are in PSI, right? I'm going to make them on KSI just to analyze it better. So if you look at this section, the slope of this line is around 23,000 KSI, right? 2200, 2300, 2600. So I know that this graph right here, it is not perfectly linear, but it is almost linear. So this equation is telling you the closest, this is the closest slope that you can get is 2 times 10 to the 6 plus 2952. So you can either use this equation and you're gonna exclude these sections. I believe the elastic portion ends around here somewhere. You can get the average of these values. But the best way is to get the shear modulus on the graph. Let's put it this way. If you want to
Which is the
which is the equation from the graph.
and that would be particularly the 2e to the 6.
That's this one.
And then what's next?
What do you mean what's next? The next? You want me to do the still for you as well? And finish the report for you, submit it? No. So the next is you're gonna do the same calculation, okay, for the steel portion. You already have the data for steel right here. You're gonna copy and paste this into your spreadsheet. I believe one of them is for steel. You don't even have to copy and paste. This is 255, 283, 416. I'm looking at the torque, applied torque values. 255, 283, 416, right? You're gonna perform the same equations, same calculations. Or even if you don't wanna do this, let's say this is my data points, right? Come here, copy. Pay attention to this one, it's gonna save time for you. And I'm gonna inflate these sections. Okay, I have these numbers, copied it. I'm gonna come here, I will create a copy of this page. I'm gonna create a copy at the end. It says aluminum data only, right? Data only. I'm gonna change it to steel. Steel specimen results. And then come here. I will erase it all. Let's see. Let's not erase it first. Let's copy this one first. What did I do? I just copied and pasted. And then I got the charts. I got the values calculated already. I got torque versus angle of twist. I got aluminum detail, but these are going to be changed. You're going to change the title, obviously. You're going to change it to steel. But your goal is to analyze the data. This one is going to be changed. And this. And in this way, you don't even have to put the equations into each cell and spend time on figuring out which equation goes to which cell. But if you want to practice, that's a good way of practicing. You're going to erase everything and start from one by one. Which one is easier?
So if I can ask, for the shear modulus, right? Like you have, like I understand, like with the tension, report, we did the exact same thing, but I was a little confused on it. I just kind of like assumed I was knowing what I was doing. But I see you stopped. Like you stopped recording the numbers. And I know that's for the plastic region because the shear modulus is only for the elastic region.
Mm-hmm.
Now, how did you know to exactly stop at that point right there, at that 1265.97? How'd you know?
Well, I didn't know. I just cut it right there. I assumed that it's at that location. But what I do usually, I stop taking the data points. I stop inputting the data points on my table on the location where this graph turns from the linear to second degree curve.
So kind of at that like second point
So
right there.
it's up to you, yes, second point. Once you get your linear like graph right here, it's not even, oh, it's not perfectly linear, but it is linear compared to this. That's the one that I use. So there is no rule of thumb like 0.2% offset method that we use on the tensile. Remember on tensile we used 0.2% method where we did where we draw a line that's parallel to the linear portion, and then and then we measure the corresponding tensile stress from the intersection point. That's the point that we accept as the yielding point. But on this one, it's not clear. But there is a relation. If you read this section, there's a connection between the relation between the tensile yield strength and the shear strength. There are no published standard values for shear strength like with tensile and yield strength. Instead, it is common for it to be estimated as 75% of the ultimate tensile strength. So if you look at this table for steel, ultimate tensile strength relationship for the shear strength is approximately 75% of the ultimate tensile strength. For yield strength, it is approximately 0.58 times tensile yield strength. So the tensile yield strength, you're going to go back to your report, previous report, and find the yield strength. If you multiply by 0.58, your yield strength should be the same as what you get on this experiment. If they are the same material, if I'm testing 36 KSI steel, let's say, right? And I want to know the torsional yield strength before I do the experiment. Usually in the industry, it is costly to run the torsional experiment, right? What they do, they use the tensile, they use the results from tensile strength, tensile experiment, and then approximate the yield strength for shear. So you can use this table. Okay. So we don't have the 0.2% method where we can determine the yield strength like we did on the tensile. Okay.
So then after you calculate that, you just stop after that number.
Mm-hmm.
Cool.
Yeah. Okay. So is there any other obstacle that's gonna stop you finishing up your report? So if you have any question right now, before you write email to me, ask me, be open, I'm gonna answer the questions. I have time right now. I can be here 4 hours. So ask me what is gonna be problem for you to finish your calculation and submit your report. You have your objective, you have the equipment that you need to use, you have the theory sections, you can summarize everything that you need to know, all the properties of the materials that's tested, and then difference between steel and aluminum. You can include it to your discussion part. You have the solution, basically. This is your solution. You can just replay the video, the lecture video that I just start recording. You can get your results for aluminum and steel and compare the two different specimens. Okay. Any question? Asking again.
No, sir.
How you feel, Andrea? Is it confusing for you? Andrea?
Much clearer, thank you.
The report should be in Word, right? Not in Excel.
Report? We're gonna make it like we did the tensile. You have your Excel spreadsheet, right? You're gonna copy and paste whatever the result and table and the graphs to your Word file. Then you're gonna come here to your Word file. You're gonna click on print. Microsoft print the PDF, print it. You can print it on your desktop. So it's gonna give you one single PDF. And then you're gonna come here. I'm gonna add this Torsion assignment. Due date is October 7th. You have 8 days. That should be enough. Save and return the course. So you have your Torsion assignment. So you can, whenever you finish, you can even finish right now because everything is given to you. You can finish in less than 30 minutes after class.
Sounds good. Appreciate you taking this time.
You're welcome. You had your handout. So you didn't, to be honest, you don't even need it. And this was answering your question also, Piero, is 0.58 times the P final from tensile test, TT. If you look at TT,
Right.
TT means tensile test, tensile experiment.
Oh,
so
perfect.
If you go back to your tensile experiment, and if you get your tensile strength and multiply by 0.58, it's going to give you your yield strength, shear yield strength right here. It's tau, y. That's what you're going to get. But you're not required to do the calculations. Our only calculations that are required for you, the one that I performed. Don't get confused. Don't go into detail too much. You can do the details when you take your mechanic design or machine design. If you're a mechanical engineer or in civil, we don't deal with torsion too much unless you are working on your PhD on structural engineering. But if you're mechanical, you're going to be dealing with torsion a lot. So this is the basic that I can give it to you right now. And that should be enough for you to understand the logic behind the torsion theory. That's more than enough, actually. So I can close the torsion. Okay?
Yes, sir.
Okay, perfect. I can close the torsion. This is the sample that I also provided. So you can, even if you cannot perform the calculations, you can just plug these numbers, plug the equations, and see if you're getting the same numbers. If you're getting the same number, that means your spreadsheet is working. So you can plug any numbers, any data from the experiment, and you can calculate the maximum shear stress and calculate the maximum shear strain. Okay. All right. It's been already 1 hour and 10 minutes. column buckling experiment. I was just putting the video together before the class, and I'm gonna go over the theory. Like I said, we are not gonna have a report on this for next week for the column buckling, but I wanna cover the essential things so you get familiarized with the theory section. Okay, what is column buckling? So let's have this one as a discussion. Let's start with somebody, Claudia. Claudia, what do you understand when you hear column buckling? Be comfortable even if you are not experiencing concrete or steel or structural.
Talking to me?
Yeah, Claudio. Claudio.
All right. What was the question? It's Claudio.
Claudio. Okay. So what do you know about column buckling? Have you heard about this term before? Column buckling.
No, I have not.
Yeah, no. Okay. What about Ronald? Ronald, you asked me a question about column buckling before the class. It's you, right, Ronald? You calling me?
No, yeah, but I don't think I did. I asked you something about something else.
Okay.
I forgot what it was.
Okay, what we saw so far, we look at the concrete, right? We look at the concrete experiments and the tensile experiments, as well as torsion. Those are different type of loading types. In the column buckling, we are actually looking into the failure scenario of the specimen that we are testing. In the column buckling, we're going to be testing different type of rods, cylindrical rods. Okay. These are different type of connections. We're going to look at different type of connections, like fixed pin connections, and I'm going to get into those type of the connections that I'm talking about right now in the next video, in the PowerPoint. We will see in general, just understand this part. There are 3 or 4 things to consider when you are designing a column. A column can be concrete column, it can be steel column, or aluminum, whatever is the material that you are using. One important thing is E value, elastic modulus. When you're designing a column, you should know the P critical, is critical load. So that load is the maximum load that you can apply to this column before it fails. When your column is in this shape, that means it's already failed, right? So I'm trying to prevent this to happen. In order to prevent this, I should determine this P critical value, and then let the people, let's say the contractors, this is the maximum load that can be applied to this column during the construction phase and then during the service conditions. The major example that we have seen was the Hard Rock Hotel. What happened on the Hard Rock Hotel? Team Ash.
It collapsed.
Okay, I'm gonna pull up something. Like I said, this is gonna be discussion more than the lecture. Hard Rock collapse. We're gonna look at the columns at the Hard Rock Hotel.
There were a lot of things wrong with the Hard Rock.
I don't want to.
How much concrete, how much support they had when they were building it wasn't enough. There's a lot.
They had the temporary supports, right? Let's look at the images.
They had them, but they didn't have enough of them.
Okay, look at this. What do you see? This is buckle, right? What did I tell you, Tim? If your column is this way, you already failed. And let's say you are the engineer. If I were you, I will take the first flight out of New Orleans, go to Europe, find a good place to live, because it's going to be multi-million-dollar lawsuit. happen. So anyway, what happens is when I say we need to establish the P critical loads, the P critical right there, critical load, I had to know how much load that I can apply to this column during the construction phase before I pour the concrete. Because when you look at this, let's look in detail. I believe I cannot look in the detail. Nope. Okay, let's focus on this. When you look at this column, if they know how much load they will be applied when they pour the concrete, on top of the metal deck, they have the metal deck that supports the fresh concrete, and you know that concrete has to be cured minimum 28 days if it's regular concrete. So you can kind of combine all the theory that we've been talking from the beginning of the semester, right? So as an engineer, you have to think the steps, what happens next, so how can I prevent the failure, this and that, and how can I minimize the overall cost, right? They try to minimize the cost, I believe, in, they were looking at the pennies and trying to cut corners, but I don't know. I don't have right to make any comments. Okay, but when I look at this, it doesn't matter it's hard rock or somewhere else, I see that the applied load to these individual temporary columns, support columns, were excessive. This is the reason it buckled. But you don't see that it is, it yielded. So yielding is different than buckling. So you have to calculate the yielding and the maximum compressive strength if it's the reinforced concrete, and see which one fails first. Is it gonna buckle first, or is it gonna crash under the compression load, or is it gonna yield if it's still, right? When I say yield, it's gonna be deformed permanently. So in this case, if it's yielded, for example, if there was not a failure, if I see the yielding, I can come and replace it and rehab the column. But this is the end of the game. They messed up big time, so there's no fix for this problem. But the overall goal that we need to learn from this incident, you should know how much load you're gonna apply to these interior columns, temporary columns, and you need to calculate the applied load on individual columns. The shoring, it's called shoring, by the way. Then see if it is enough. If it's not enough, then you need to increase the amount of the interior columns, or you need to increase the diameter of the interior column, or you have to change the type, material type of the interior columns. What else I can change? Diameter, length, because if I make it shorter, it's going to be more durable, right? So this concrete, this column buckling is more related into the parameters that we can change. We can adjust it to increase the critical load. So I can bear my design, my column that I designed can bear more load than that is like it can be optimized. Let's put it this way, if it's clear.
I have a question actually about like if you were designing this building, right? So you know how much, like, I guess when are we going to start seeing problems like coming up in our classes where it's like we're going to see actual structures like this, like some examples like this, like if you're designing the floor of a building, how do you know how many concrete like columns to put? How do you know how many steel columns to put? Like I guess when are we going to start seeing stuff like that? Because to me, I look at.
Are you junior or sophomore?
Junior.
Junior. So are you civil?
Mechanical, but just curious.
Just curious. So if you're a civil, you should, you will see the structural design course when you are junior after taking mechanical materials. And there are codes that ASCE, American Society of Civil Engineers, they published the publish the international codes and the nation and the city codes. Let's put it this way. Let's say if you are designing a hotel, you have different loading scenarios for the particular section. Let's say for the kitchen. Let's say for the rooms. Let's say for the conference room. So these loads are based on the statistical calculations. They know in average, how much load that can be applied on this particular section, and they are using the other equation that I cannot think on top of my head, but they input these parameters such as the maximum occupancy. For example, if you're designing a theater, you're going to look at the maximum occupancy. How many people that you can fit in this theater. If you're designing a library, then you have the dead loads from the book. Or in the other case, if you're designing a certain section in the hotel that's going to carry the AC units, that's going to be the point load, the huge point load that will be applied to a certain section that you have to add additional columns and additional strong durable girders, beams to support that load. Is that make sense? So you have to the load where the load starts, and then how it's distributed, and how it goes into the foundation, from top to the foundation. And I was looking for my thesis for my master's. I did my thesis on high-rise structures. I work on the 60-story building in downtown, and we mainly deal with the wind loads. We don't have seismic loads in New Orleans. I designed it against the hurricane, 500-year storm. It was 160 mile per hour winds, 160 or 150 mile per hour. And I was checking the torsion. This torsion that you will deal with this torsion when you are in your master level or your PhD level, you will look at the torsion and even the column buckling in details. But in general, you just enter the values that's provided on the ASCE manual, and then the software automatically calculates how much load will be applied to the certain section of this story. Let's say if this section was for the rooms, you have 140 or 200 pounds square feet for each room. If you multiply 200, let's say 200 PSF, pounds square feet, with the square footage of the room, then you know how much load is applied. Let's say this is your room, hotel room, and this is the area. And let's say you have 1,000 square feet, right? It's gonna be basic. I'll keep it basic. And if ASCE tells you prescribe if it is 200 PSF, which means every square foot of this hotel room is going to experience 200 pounds, right? 200 pounds. And if I want to know the overall load, total load, what do I have to do? I know the area in square feet, and I multiply it with the 200 PSF. That's going to be the load.
What are you doing? What are you?
And then based
doing homework with Trey.
Hello?
Oh, okay.
Can you please?
And Grant's doing his homework.
Yeah.
Give me 1 second, guys. Let me mute everybody. Okay. So this is the total load that's applied to your section, to the specific room that's 1,000 square feet. Then you have to calculate how many girders, how many beams, interior beams that you need, and then you have to determine how many columns that you need, and it's based on the architectural drawings, you know. So first you look at the architectural drawings, and they're gonna tell you can place a column at certain locations, and then you're gonna increase the size of the column and the length of the column based on the given load. But this is how you determine your load. Piero?
Yeah, I'm listening.
Okay, okay.
That's cool.
Okay, that's how you overall, this is the big picture, okay? You have to know the load path, how the load is flowing from top, from roof to the bottom. And then you can size up your girders, your interior beams. These are interior beams, by the way, right here. And you have your girders, bigger size beams. So the load from the slab, it is carried by the metal deck, and then it is transferred to these interior beams, from interior beams to girders, from girder to the column, the big column. You have a big column right here. But these are temporary shorings that buckle, and the only purpose of the temporary shoring is to handle the load coming from the fresh concrete, because concrete, it takes 28 days for concrete to bear 4,000 psi stress, and it's 3 to 4 days to bear its own weight. So for the 4 days timeline, you should have exterior support to carry the load coming from the fresh concrete. So the mistake was they didn't provide enough shoring, enough columns, right? So they didn't distribute the applied load evenly to the columns. They were in some cases, and the length, if the length was shorter, for example, in this case it's impossible because you already know the depth or the height of each story. It's impossible. But instead of, for example, the steel that they use, if this was cheap steel, 36 KSI, they could have used a better material with higher strength. This will increase your critical buckling load. Or they could have increased the diameter. If you have thicker, sturdy material, sturdy column, you could have prevented this buckling. This is all I can say on this Hard Rock Hotel case. So this Young's modulus, that's where I mentioned that better material, the stronger material, it will come with the high Young's modulus. It's going to increase the critical load because it's in the numerator. And area moment of inertia right here. And I'm going to ask this question to Memi or Celine. Celine, I have a question. How can you calculate the moment of inertia if your section is rectangular? I'm trying to calculate the moment of inertia. How to calculate the moment of inertia? Rectangular section. You learn this in statics, you learn this in mechanics of materials, and you can pull up this equation from the mechanics of materials book. When I say rectangular section, let's say this is my rectangular section. I'm waiting for your answer, Celine. Can you hear me?
Celine texted me an hour ago saying she had a really bad migraine.
Oh, okay.
Yeah.
Okay, Mimi.
I'm here. I'm just slow.
Okay, I'm gonna continue with you then, Mimi. Hello. Can you hear me? Okay, then I will go with someone else.
I mean, isn't it just an equation? Isn't the polar moment of inertia
Yes,
just an
equation. You have your base, let's say 2 inch. You have your height, 2 inch. Let's say this is 4 inch. You can easily pull up this equation from your mechanics of materials book, or you can look up online right now. I have 40 students. One of them should be able to tell me how to calculate the moment of inertia for rectangular section. It's
Is it
simple.
1/12 base times height cubed?
Who is this? Piero?
Daniel.
Who is?
Daniel Dockhand.
Daniel Dockhand? That's perfect. That's the answer. Okay.
Can you say what that equation was again?
This is the moment of inertia equation for rectangular sections. It is base BH cube over 12. And you should be able to calculate the moment of inertia for the circular sections. And the equation is here, pi d to the 4 divided by 64. This is what you need for this experiment, because we're going to be using circular sections. But I was going to give you a simple explanation how you can increase the moment of inertia, because where I was coming at, my overall goal is to increase the P critical, right? I can increase the modulus of elasticity if I use the stronger material. Instead of doing 9,000 KSI for steel, I can have stronger steel or different material. And I can increase the moment of inertia by increasing the diameter or by increasing the moment of inertia. And how can I increase? I can increase the height, I can increase the base. If I increase the overall cross-sectional area, it's going to increase the moment of inertia, right? So in this case, if I make, let's see, I'm going to do a couple calculations, and you're going to see how we can optimize the moment of inertia. So I have base two inch and height 4 inch. So my base times height cube divided by 12. And its unit will be inch to the 4th. So in this case, my base is 2 inch and height is 4 inch. And the other scenario, my base, just put this way. Make the base 3 inch and the height, let's say 8 inch. Let's see how it's going to change. This is scenario 1. This is your scenario 2. My base is 3 inch. Perfect. 3 and 8. So 128 inch to the 4 versus 10 inch to the 4. I just increase the cross-sectional area, increase the height and base. Same way, if it was circular, if I increase the radius, the diameter, which is going to increase the cross-sectional area, it's going to also increase your total moment of inertia in this equation. So once you increase this, what's going to happen to this equation? P critical. It will also increase. And you will see when you run your equations. And I'm going to run these equations real quick. Let's see. Pi for E, I'm going to keep it to a 900. KSI for LE, I'm going to keep it 1. This is the effective length factor, by the way. We're going to get into this in a second. You're looking at this equation right now. And I'm trying to maximize the P critical. And then I have the moment of inertia. What else is missing? E is there, modulus of elasticity is there, and the moment of inertia is there, and P critical. Okay. So 3.14 square times 39,000 KSI times moment of inertia divided by LE square. I get this number. It should be in pounds. So this is the first scenario, scenario 2. Let's say this is scenario 2 because I use the number, the moment of inertia from scenario 2. And I'm going to look at the scenario 1 right here. Scenario number 1. Modulus of elasticity is going to come from the scenario 1. And P critical is less than what we got right here. And if you want to clear it up, this is all border. Let's divide these numbers by 1,000 so we can keep it in kit, and it will be easy for you to compare two numbers. So this number is bigger than the scenario 2. The P critical based on scenario 2 is 36,598 pounds. In scenario 2, it is 3,049. Correct? So what I did was I increased the size of the member I bump it up to 8" in height, and base is just increased 1 inch. It's gonna cost some money when you look at the amount of material that you use, but it's gonna increase the capacity substantially, right? So what I was trying to explain, there are different parameters that affects the critical load. One was the material type. It will change the modulus of elasticity. The other one is the material cross section, the members cross section. It will increase the P critical or decrease the P critical, depending on the size increase and the size shrinkage. And one more thing is important is LE. I assume that it's 1, but there are different values that we need to assign, right? And we're gonna look at these values in a second. So I'm gonna take a break, 5 minutes. I have to get water. Give me 3 minutes. And I'm gonna wrap it up in 20 minutes. Give me 1 second. Okay, everybody's here, huh? Can you guys hear me again? Lee?
Yeah, we can.
Okay, I'm gonna wrap it up real quick. Let me share my screen again. Okay, so we learned how important is the moment of inertia, right? If you play with the cross-sectional diameter or the height and the base, if it's rectangular sections, we can increase and decrease the moment of inertia, which will indirectly affect the overall critical load. So by doing this, we can jump into my video that I tried to make it before the class. And I believe there is no question on this failure type. Now everybody knows that we can eliminate this failure by increasing the modulus of elasticity of the material type that we use. We can change it, or we can increase the moment of inertia, or we can change the type of connections. So let's look at my PowerPoint. Okay. So this is the video that I tried to make it. If I can finish it, I will finish it. If not, we're gonna look at it again next week. So in this video, we're gonna look at which columns that you will see in a second, which column is most likely to buckle. There are different type of columns, different type of configurations on the connection types. The first one we will see is pin-pin. It's pin connection on both ends. And this little signal here, it means right here, sorry. This little signal that you're gonna see, the red circle, it tells you the connection type, it's pin connection. And when you think about pin connection, you guys are already seen and you guys work on the problems that has pin connections or fixed connection. So what do you understand when you think about the pin connection? What it tells you? I'm gonna ask this question to who? Answer.
There's components, right?
Well, what you're gonna have when you say components, what do you mean components?
Well, it's not going to move in the X direction, right? So it'll only move in the Y direction.
Well, let's look at it in details. Your close, it is restricting the rotation. I'm sorry, translation. You're not going to be able to move on the X and Y direction on XY plane, but it's allowing you to rotate. So there is no restriction against moment. You will see, you can imagine, you can picture it like it's a rod being held in your fingers, like this. So you can picture it like this. So this rod, it's able to rotate, it's able to translate, let's say this thing. It's able to rotate, there is no fixed connection at the top, but it cannot translate, it cannot move on the X direction because I'm holding it, right? As opposed to I'm holding and grabbing in my fist. If I hold it like this, how it's gonna move, how it's gonna rotate. And if it's fixed at the bottom, there's no way to move and rotate. These are different types of connections. This is the first one is pin-pin. It cannot just rotate. So there is no moment at this location because it's not fixed connection. When you try to rotate, if there is a moment applied to this column, it will try to rotate. Okay, and the moment connection on one end right here, and the free connection on top. And we're gonna look every single of them. We're gonna look at the real life examples as well, where they use this type of connections in structures. So this is moment and free connection on the top. And you have moment connection on both ends. And the moment connection will be more like the rod being held on your fist, like I explained before. You will see in the screen right now. So in this example, it's not moving, it's not rotating, it's fixed. And if there is a moment applied, you're gonna have same opposite moments applied by the system. So which column is most likely to buckle? Think about it. You got a couple of minutes to give me your answer. Pin-pin connections, moment-free connection, or moment-to-moment connection. Which one is going to fail or buckle first? So we are assuming that each specimen, each sample that we are testing, it has the same modulus of elasticity. It has the same diameter, it has the same length.
Is it the double pinned connection?
No. You're close. What other answer? Any guess?
Is it the third one because there's it's fixed to fixed position? No.
That's
well, the second one.
The second one, exactly. So the answer is the one that the moment connection on one end and the free or no connection on the other end. This one in the middle.
On a pin reaction, there's only one reaction, right? Like in a pin, in like a pin, there's only one reaction. There's not an X and a Y. There's just only one, right?
Right. So this one, moment and free, that's gonna be the one that will buckle first. And you will see why it's effective. It's all about the effective length. LE, L sub E, that I assume it was 1 on my previous calculation. I was just comparing the moment of inertia, different moment of inertia on different scenarios. Now I'm looking at the LE factor, how it will affect this LE factor. This LE effective length in different conditions, pin, fixed free, and fixed column. Your K values is different. And if you multiply this K by L, it's going to give you your LE. And these are on the equations. Effective length, K multiplied by L. So let's continue. So we have different type of column and connections. We're gonna walk. I will walk you guys through each case. So we can brace the column in different configurations. In the first one, we have fixed. The first one, moment connections. And then we have pin and fixed right here. And this one is one free end at the top, and you have fixed at the bottom. And then you have fixed for rotation and free for translation, and pin at the bottom. And these are the ways that they will buckle in the case of failure of simulations. Okay, so the K values for column buckling. You're going to see how they are effective. Let's look at the first case scenario, scenario A. When you look at the A, you have fixed up at the top, and you have fixed at the bottom. And imagine you're grasping from both ends. They are fixed, and you're applying force. It's going to be hard to buckle the column as opposed to pin connection, because you are holding it from 3 different axes. And on the B, you have pin connection at the top and you have fixed at the bottom. And you can see on the left side how you have to picture on your head. And the third one, this is the case, let's see. You have something that's rotation fixed, that's fixed for rotation, so it cannot rotate, cannot take any moment, but is translation free at the top. And you will see when you can use this type of connections. And then we're gonna look at the D. D is pin connection. It's more flexible and it has less P critical load. And you have E. On the E, it is it's something that is fixed on the bottom and allowed to kind of move around the top, and it's fixed at the bottom. And the last one is F. It is free to move at the top, but it's fixed to rotate. At the bottom, it's pin. But don't worry, we're gonna only look at the two different scenarios on our lab report. We're gonna be looking at the fixed and the pin. So the first one, A, and the pin connection, D. And let's look at these theoretical K values. So 0.5 is for the fixed connection, 0.7 for the pin and fixed connection. And if it is free at the top, free for translation and fixed for rotation, K value is 1. That means you're going to multiply the length, overall length of this column by 1. And D is 1 as well. This is the pin. So these two, the first one, A and the D, those are the ones that we're going to use in our experiment, in our calculation. The rest is for your reference. So if you look at here, if you increase the K value, it will more likely to buckle. So if it's fixed, you have the stronger column against buckling. If it's fixed on one end and pin on top on the other end, it will be more likely to buckle compared to the first scenario. And it will go up to 2K in the case of free at the top and fixed at the bottom. So this is your overall length of your column multiplied by the K value. You will get your effective length. So when you look at this first scenario, scenario A, you have fixed connection at the top and bottom, and from the table your K value is 0.5, and you're trying to calculate your P critical based on the dimensions and the material type that's given. And first thing first, you need to calculate the effective length. So K is 0.5, and if you assume that this is 10-foot long column, you're going to multiply 10 by 0.5. And this column is going to behave like it is 5-foot column. This is exactly how it's going to behave. And let's look at the second scenario. In this scenario, you have again same length, 10-foot long column, and you're going to multiply this by K value from the table, 0.7, because it's fixed connection at the bottom and the pin connection at the top. And your column is going to behave as 7-foot column. Same way, as you increase, it's going to increase the effective length. And what happens if you increase the effective length? From this equation, if the effective length is increased, let's say LE, that was 10. When the effective length is increased, the P critical is decreased, right? Am I correct?
Yes.
Right. In this scenario, let's make both 10. And I'm gonna add one more thing right here. Compare the scenario 1 and scenario 2. In these scenarios, I'm gonna keep the moment of inertia same. I'm gonna assign it 128. When I assign this 128 inch to the fourth. I have K value. I have K value. Doing 9,000 KSI for both scenario 1 and 2, and the K value for this one, let's say this is pin connection. Pin. I need to add one more thing. It's going to be the original length of the column as sub 0. Let's say this is 10. I'm going to calculate LE, the original length, multiplied by the K value. I do the same thing here. In this case, it's going to be fixed. And the length is the same, 10. Perfect. So which one is higher? Which one is higher capacity? Scenario 1 or scenario 2? I use the same material. I use the same dimensions for the column. They're both 10 foot long, right? And the moment of inertia is the same. I'm using this one. Base is 3 inch, height is 8 inch. There is no difference on the column type, but the only difference is the connection type. So if I change the connection from pin to fixed, I increase the capacity, critical buckling capacity. Right or wrong? Tim?
Yeah, that one's definitely much larger.
Much larger, right?
Yeah.
So what did you learn from the first 2-3 trials? I play with the material type. I can change the modulus of elasticity, use stiffer material, increase to 35,000 KSI, and I can increase the P critical because this E is on the denominator, on the numerator section of the equation. And I play with the moment of inertia, play with the base and the height of the cross-sectional dimensions. And I learn how to optimize my section. I compare 2 different scenarios, and then I kept everything the same. Modulus of elasticity, the length, and the cross-sectional dimensions. Everything is same, but I start comparing the connection types, different connection types. If I make it fixed, I increase the capacity of my column. So in this case, it's going to be able to bear at load at 1,464 pounds as opposed to 366 pounds. There's a huge difference. Then you can ask yourself why we are not using fixed connection all the time when we are designing a structure, fixed and pin column. Who's going to give me the answer? Why we
Is it cheaper and easier to use a pin connection sometimes than you need to? Like, is it cheaper and easier sometimes to use a pin connection over fixing the rod, through, I don't know, welding or something else?
Who is giving the answer?
Tim.
Tim, perfect. That's the answer. So it is hard, it's time consuming, and it's costly to have fixed connection. Like I said, you're going to see in the video at the end, you're going to see real life examples of the connections, pin, fixed. You will see you need to use extra bolt. You need to use welding, additional welding in order to make it fixed. Okay, so it's costly. It consumes more labor. It requires more labor to do the fixed connection. And in some cases, you need flexibility. If you're in the seismic zone or if you're in the hurricane zone, you need to give some flexibility to your design. So you cannot assign fixed everywhere. Otherwise, it's going to be more fragile design. So if you have some flexibility, it's going to move and it will come back to original position because it's going to be moving on the elastic region. Make sense?
Mm-hmm.
The first reason is the economical reasons. It's expensive, it's costly to have the peaks fixed. Okay. Okay. But if you have free ends, you see how you change, you increase the effective length of your column substantially, you multiply them by 2. And you will see when you're going to see these type of cases. So, Tim, do you have any, can you give me an example of this type of connections, like where you can see the fixed at the bottom and free at the top?
Flagpole?
Perfect. Did you study your lesson, Tim? Did you look at something before the class?
No.
Flagpole. Yes, it's a flagpole, exactly. It's fixed at the bottom and it's free at the top. Or you can see the energy towers. Or if you look at the skyscrapers, high-rise structures, they are acting as a fixed connection at the bottom and free at the top. In the case of Burj Al Khalifa on Dubai or the Empire State, etc., they are fixed at the bottom and free at the top. Recommended design K values. You don't need to know these values before you get to design class. These are for, let's say if you're working with wood and different type of material, you can look at the recommended design K values and adjust the effective length. That's when you need it. Okay, so this is the rotation fixed and translation fixed. So if you look at this, it circles. The first circle at the top, at the flanges. So at the flange, let's say this is my beam. I'm holding it at the top. So it's not able to move, it's not able to rotate at the top. I have 3 extra bolts on one side and I have 3 extra bolts on the other side. And I have 3 bolts at the top, at the bottom as well. 3 on one side and 3 on the other side. So if I'm trying to apply load at the top, if you guys are able to see my camera, I'm trying to show something. So if you apply a force at the top, those connections, those 3 bolts at the top, it is eliminating the rotation. So it's fixed at the top from the flanges. This is your flange, and this is your web. The middle section is your web. And the web section, you are connecting this beam to the column from web to web connections. It's connected to the web of the column. So it's not able to rotate, it's not able to translate to any direction, X, Y, Z, 3 dimensions. If you want to keep it simple, if you want to have pin-to-pin connection, you can just remove these 3 bolts at the top and 3 bolts at the bottom. On both sides, it's going to be pin connection, right? You can assume the same type of connection for the columns as well. Okay, if you look at here, rotation fixed and translation fixed. So it cannot move, it cannot go up and down, and it cannot rotate. What about rotation free and translation fixed? So if it's rotation free, if I'm applying a moment, it's able to rotate, right? I'm applying a moment. I have, let's say, 1 bolt from this side, 1 bolt from that side. It's not going up and down because bolts are in shear. It's holding the entire beam, right? But if I apply a moment, this is my lever arm, and I have a load applied here, let's say 10 pounds, and I have this one is, let's say, 1 foot. It's 10-pound foot. Moment force is applied, and there's nothing holding here. But if I do this, if I'm grasping from each direction, and I'm applying the same force, what's happening? I have the equal and opposite moment right here, right? You should learn this when you go to structural design or machine design. It's not my job to explain this in detail, but it's important to remember, and it will help you when you come to the machine design and structural design. So in this case, what happens, you are saving from the cost. That's pin design, pin connection. You only have 3 bolts. You only need less labor as opposed to the fixed connection. Okay, let's look at the other case. It's coming. Like you see, it's not moving because these 3 pins are holding it, but it's rotation free. Even though you have 3 bolts, imagine in the scale, the large scale of the project, these 3 bolts are nothing to restrict the rotation. Now we're gonna look at the rotation fixed and translation free. Okay, this rotation fixed and translation free. This case, you can only see in around California if you're in the seismic zone. So these connection types at the bottom, it is allowing your columns or the foundation to translate on the XZ plane, but it is restricting the rotation. This is important as well. And in this case, you have to change your K value. This is the example. If you look at the screen, you will see the real life example of the translation free, rotation fixed connection. So this is the seismic footing design. So this allows your design, your columns or your footings to translate on the XZ plane, but it restricts rotation. You don't want your structure to be overturned, right? I don't know if you're able to see the simulation, like this is moving. You can see it's translating when the earthquake hits. They will sway sideways, but it's not gonna rotate. So this is the answer given by Tim Ash. The question was the example, real life example of rotation free and translation free at the top. And you can give an example of the American flag. It's high up top. It is free at the top. It can move, it can rotate, nothing is holding, right? There is no restriction at the top. One detail, let's go look at this close. As you go down, this structure is tapered, right? The diameter at the bottom, at the footing, it is large, and as you go higher and higher, diameter is reduced. It's tapered design. What will be the reason? Simple. To answer, like there are 2 reasons. Any guess?
Is it so there's not as much weight at the top, so the base is a lot more sturdy? All the center of mass is at the bottom?
Well, quite close. So first of all, you want to reduce the overall load, overall weight of your design, right? You don't want to also carry the load with self-weight from the structure, right?
Okay.
The self-weight of the structure is going to be the weight of the steel member, plus you're going to have the load coming from the wind or the seismic load, whatever, that's going to be applied to this pole. Let's say this is my pole. I have a flag right there, and now you have the wind force applying to the surface. And if you convert the point load, it's going to try to rotate it, right? This way or that way.
Right.
and I need to calculate the overall moment at the bottom, and I have to have equal and opposite moment at the top, at the bottom. Whatever is the moment applied at the top has to be counteract at the bottom. So in order to get that moment at the bottom, I have to increase the diameter. If I increase the diameter, I can increase the moment of inertia. If I increase the moment of inertia, it's going to compensate the applied moment to your structure. This way, I'm going to also eliminate the surface area, because if I have more surface area on this pole, it's going to be it's going to receive more wind load because surface area is increased. That's why when you look at the high-rise structure, they are reducing the surface area as they go up higher. This one, for example. This was the question that I was going to ask, but I answered the question. So when you look at the bottom, it has more area, diameter is more, or the square footage is more. And if you look at the top, it is less. First, you reduce the applied load caused by the wind forces. Second, you need more moment of inertia to compensate the moment applied by the wind. Okay. Or you can look at this one as a, if you change the orientation, you can look at it as a cantilever beam. Instead of this high-rise structure, I change the orientation. I have fixed at one end, that's a cantilever beam, and I'm applying a point load. It's going to create a moment right here. And sometimes you always solve this problem, a basic static problem that you solve. And then you can size your beam, you can size your column. The column design is similar to beam design. It all depends on how you picture it, how you look at the orientation. Okay. All right. This is what I have to say for the column buckling. And then I'm going to explain this column buckling again next week. And I'm going to work out these examples with the measured data from previous year. I might have different diameters, like I show different scenarios. These are the simple version of explanation of the column buckling. In the experiment, we're gonna have 1, 2, 3, 4, how many? We're gonna have 9 different samples, 10 different samples in different diameters. As you can see, one of them is 0.26, 25, 19, which is gonna tell me the effect of the diameter, how it affects the increase and decrease on the diameter, how it's gonna affect the peak critical load. If I increase the diameter, is it gonna increase the peak critical load or decrease? What is my gain, etc. And the length, how length affects the column capacity when it comes to buckling, and different connection types. Like I said, we're going to look at only 2 different kinds connections. First one was the pin. In this case, K is 1, and you have fixed. K is 0.5. What we do is during the experiment, let's say this is the UHDM, and I have my specimen. I'm applying the buckling load. It buckles. When it buckles, I take the measurement. As soon as it buckles, I see the buckling. You can see with your eyes without looking at the data. Whenever it buckles, you stop the experiment. You take your measurement, it's 281 pounds. So this specimen failed at 281 pounds. And then I go to the second one. This is the diameter is 0.25 and the length is 23.5, and the connection type is the same, fixed, so it's 0.5. This one is 224. So I see that diameter change reduced and the length reduced, and you see that the compression load is also reduced because you have reduction on your diameter, on your cross-sectional area. Increase in length will reduce your compression load, your critical load. You will see when you look at the 18-inch sample and 23.5-inch sample. So in 23.5, if your length is 23.5, you have 224. If you have shorter section, you have 414. So in order to buckle this specimen, you have to apply 414 pounds. Is that clear? Piero?
Yes, sir.
Understand the difference, I tried to explain these scenarios over here. So after looking at these different scenarios, how we play the numbers, the moment of inertia and the length and the modulus of elasticity, and this makes sense. So this comes from the experiment, right? I'm gonna highlight this. Okay, you got this from the experiment. And you have to compare this with the EBL value, elastic buckling load.
That's as soon as it buckles.
I show you guys how to calculate the EBL, elastic buckling load, with this equation, right? So if I know the diameter, if I know the length, if I know the K value, and if I know the modulus of elasticity, nothing is holding me to calculate the P critical. But this is theoretical number. I have to compare this number with the experiment and see how it differs. You know, and then you can calculate the percent error. Pretty simple. But the idea was, like, if you think about it, when you compare these two numbers from the theoretical equation and the experimental value, you're gonna forget it's not gonna give you something in result, like at the end. But the most important thing is the first three different scenarios: the change in the diameter, change in length, connection type, and the change in modulus of elasticity. Those are the parameters that you can change when you are designing, and you can optimize your design. If you can save 10,000, 50,000 in a design to your boss, you get the promotion. And the best way is to play with the design and optimize it is the moment of inertia and the connection type. That's where you're gonna put your engineering skills and your judgment. How can you change the orientation? How can you change the load path in a structure?
The support.
Yeah, change the support type, etc. So this is from the experiment, and these are the calculations. Okay, this is different sections. Let's put this one as this. Okay, so this is constant 29,000 psi or 2,900 to 29 million psi, and the modulus of elasticity is changing because the diameter is changing, and the E is constant. EBL, basically the same equation. If you plug this equation right here, you're gonna get your elastic buckling load. Like, you know, this elastic buckling load is in the elastic region. If you go beyond this elastic buckling load, you're gonna deform your column permanently, which you don't want. And you see in the example on the Hard Rock Hotel, on the picture, it was buckled permanently. So 445 right here. Let's compare these error is 36.9%, which is a lot. Probably the measurement was not correct. Measured maximum compression load was not 281, it was something else. I missed it, or my technician, he missed it. Over here, you have 43%, 38%, 50%. Only these values right here, they are close, but rest is not close enough.
Why is it negative?
Why
is it negative? It shouldn't be negative, right?
It will be negative. It has to be absolute value, so it has to be positive. You have to change the equation, or just multiply by negative. But it should be positive all the time. Percent error should be positive. It tells you there is 50% error. This is almost half of what was calculated. But that was last year. Maybe while I was playing with numbers, I changed the values. So I'm around the experiment again this week when I go to campus. I will collect this data points and I will share with you guys. But other than that, without looking at the percent error, did you guys understand the logic behind it?
Yeah, I just think it was a lot.
What is it?
Yeah, we understand it. It's just a lot to all take in at once.
Yeah, it's a lot to take. That's why this class is recorded, so you can go back and look where you get confused, and then call me instead of email. A couple of you guys call me time to time. I answer the calls, rather than when I see the email is complicated. I can't answer the email from my phone if I have an equation that I need to explain, or if I have something to explain. You know, it's time consuming for me as well. So if you can't get an answer, just give me a call, like other people, students. But I try to make everything clear when I'm teaching, so when you're doing your report and calculation, everything is straightforward. And even your numbers are not similar to what I have calculated, that means either you're doing something wrong or I explained something. But so far, everything is working out. You know, with the torsion, I work out the examples and the numbers were okay. And this one, percent error, it is, and some of them is higher. But like I said, this might be due to the typo. But overall, this is how you calculate. So once you get your data, if your percent error should be around plus or minus 10% from the measured maximum compression load. And you have the procedure. And if you want to look at the examples, there were one example that I found. We can look at this one. And this one is the buckling failure of a pin and column of low slenderness ratio. Slenderness means the height to diameter ratio. If it's long and slender, it means it will buckle quick. And you can see how it will buckle. If you see this laser, I don't know if it's clear. You will see how it will buckle. This is the cross section, by the way. The material properties are given in the English units, 275 Newton millimeter square. This is the yielding stress. And this is the type of connection. You have pin connection at the bottom and pin connection at the top, which means this roller support, it can go up and down. But in this case, we are applying compressive load, so it's going to only go down instead of going up. We're not applying tension load. This is your loading diagram. I mean, it cannot be perfect than this. Look the way it's buckling. You can still see the original laser. the line coming from the laser, and it's already failed. And you can see that there's a buckling. It's called local buckling, right here in the middle, in this section. So in their case, they are using this cross section. It's a hollow cross section. There's nothing in the middle. It's a hole, just a hole, and the thickness of the wall is 2.5 millimeters. But in our case, we are using solid circular sections. You can calculate the moment of inertia of this given section as well. If you look at your mechanics of materials book, you can get the moment of inertia equation easily. Okay, if there's no question on torsion, on buckling, we can finish our class. But if there's any question, I'll be here to answer the questions.
Thanks for today's lesson.
You're welcome. Okay, also midterm. How is the schedule for everybody when the midterm starts? When are the midterms are starting?
I have no idea.
Yeah, I mean, I know I have a midterm coming up on the 6th, and I also have 2 tests on the 13th. So, you know, every other class in engineering is kind of saying, screw all the other engineering students right now. And they're just kind of piling on tests all on the same day from what I've noticed, because I've definitely had a couple tests already on the same day.
Okay, let's see. Mine is not going to be too hard. It shouldn't take more than a couple of hours. Open book, open notes. Taking into consideration, open book, open notes. Whatever you have seen on the notes sections, they are not going to be different than what you have on the Moodle. Let's see, fall break, happy holiday, October 14. Test is October 17. Actually, this production line test is replaced by the column buckling. The only reason I replaced it because we know the production line test equipment is, I think it needs to be upgraded. That's what I heard from the department. So they need to upgrade the software. And until the next notice from the department, I'm gonna postpone this to the end. But like I said, we still have time to finish all the experiments. And this is the only experiment that students have hands-on experience. The other experiments that I don't even perform individually, like by myself, because the equipment that we use they're expensive piece of equipment. This one is the only one that students are hands-on experience, but it is super simple. All you do is you take samples from the same pool. We have aluminum, copper, and steel samples, wire samples. Each students take samples from each spool, and then you test it under tensile, each wire, and then you measure the failure load when it fails. Let's say it fails at 100 pounds, and then I take my sample, and my sample fails at 100 pounds. And then team gets his sample from the same spool with the same diameter. You assume that it's the same diameter because it's advertised on the spool. And I measure it, and I get 98 pounds. And then Andrea gets her from the same spool, copper, same material, she gets 97. We look at the standard deviation, and we look at the statistical analysis of the results, and then we calculate the standard deviation for the samples that we test. In the worst case, even the software is not working, I will cover the lecture. It's not mechanics, it's not into mechanics more, it's more into statistical analysis. But you're not going to be responsible for the midterm. So this one, you can just avoid this, and you can wait for this one till final exam. But what I will cover on the midterm, I'll cover the tensile test. I'll cover the concrete experiments. Torsion will be included. And then column buckling will be included. If you're able to perform the calculations on the spreadsheet, and if you know which equation to use in which case, then you should be okay. Like taking into account that it's going to be open book, open notes, open everything, you should not have any problems when it comes to calculation. But when it comes to answering the short answer and long answer questions, I will throw the questions, let's say, how to increase the capacity of a column, for example. I just explained today, the entire lecture was on how to maximize the capacity, column buckling capacity. Maybe this is where you're going to mention the moment of inertia, how it contributes to capacity of the specimen or the member, structural member. You're going to talk about the modules of elasticity, how it contributes to material strength. You're going to talk about the connection types, you know, different type of connection, different type of configuration in regards to connections. These will increase and decrease the capacity of the column. Same way on the concrete compression. What are the ways to increase the capacity of your concrete sample? Curing time, temperature, the water cement ratio. If you add more water, you're gonna reduce the capacity. If you have less water, it will increase the capacity, but it will reduce the workability because it's gonna be hard to work with the concrete.
So I have a question about your dates then.
Yes.
So next week, so today's September 30th. Next week, we'll be doing the second compression test. So that would be October 7th. And since we technically don't have fall break, am I wrong on that, guys? So the 14th would be the exam?
Okay, let's do this. Let's make the 14th is the...
I just want to make sure, am I right, guys? Do we not actually have?
I know we don't have a spring break. I know we have a Mardi Gras break. I don't know about a fall break, if I'm being honest with you.
We don't have a fall break.
Okay, there is, yeah.
To my knowledge, our fall break is just the Thanksgiving break.
Right. Because we're not supposed to come back after that.
Okay, let's do this.
I mean, to school.
Let's do this together so everybody's on the same page. So I don't get confused because I'm going to finish this one in 15 minutes. If you guys want to leave, you're more than welcome to leave. You have to catch another class. But I'm going to finish this syllabus so we can follow this syllabus up until the midterm, and then we can look ahead or schedule. So production line test, we are not having this. We already have had our column buckling test. Right, we got the torque test, torsion test. And the next week, we're gonna have the second compression test, right?
Correct. So you need to basically move them all down one.
Okay, wasn't too bad.
I mean, at that point, it doesn't really matter.
Yeah, that should be.
Okay.
And I don't remember what day we actually missed, so.
That's okay. Like I said, we had three weeks for the hurricane makeup every semester. So we still have time. We are almost, like, I will get to that. Let me see what we have left over. And I might take a break when we have the baby. So I'm expecting in 2 or 3 weeks. I have to be busy. I should be, helping my wife. It might be in 3 weeks. Maybe we might even be done in 3 weeks, because what we have left is midterm exam. Second compression is going to be next week, and midterm exam is the following October 14th, and then we're going to have beam bending, right?
Mm-hmm.
This shear and hardness test and review. This is just going to be the review. I'm not even going to have the Zoom meeting, but I might have the review before the midterm and cover the shear and hardness right there. That's what I usually do, because we don't have any experiments on shear and hardness. It's just a review every semester. I provide the handouts, and students are not responsible for the shear and hardness on the final. So I can push it back before the final exam. And the production line can be right here. So far, we got tensile test done. Concrete is almost done. Next week we will finish it. Column buckling is, I will complete the column buckling, provide the data. I will run these calculations again for those of you who wants to see it again, how to develop your reports and develop your tables. There's no graph on the column buckling. You're lucky. So torsion is done. Once we have the midterm, October 14, October 21st is beam bending. I love beam bending. We're gonna spend quite a bit time on beam bending. It's interesting. And then we're gonna have the production line test. Like I said, if the software is up and running on this equipment, I have to test 40 different samples by myself from the same school. When I say school, I'm gonna explain that too. 1 second. Oh, this is what I did for last year. A lot of statistical calculation. It's going to be pain for you to develop this graph, but I'm going to spend time to explain how to develop this graph based on the data that we're going to have from this wire tensile test. It is super simple when it comes to measuring the data and calculating the breaking stress. Same equation, P over A, that's gonna give you the stress. But when you come to the section that you're gonna work with the mean, standard deviation, and developing your standard normal distribution and probability histogram, that's where you get confused usually. But before this section, before we get to here, I will share a PDF or a video at least from different source, so you have familiarity with the normal distribution and probability histogram. Before you come to class, you should be able to familiar with these graphs, how to calculate the normal distribution, etc., etc. And this one will be on Moodle as well.
That's way later though.
That's later. That's later.
Yeah, that's
later. That's later. But again, even for this one, you're gonna have the Excel template for you, ready for you to start your report. With that being said, we're looking at the schedule at November 11. If everything is perfect, we should be done in November 11. I don't know when is the last day for class. November 11. Let's say in the worst case, November 18.
Sounds good.
If I have something going on, if I get sick, by the way, I had to take COVID-19 test yesterday. I was sick for the past 3 days. That was the other reason that I wasn't able to answer the emails. I didn't have anything. I didn't have any symptoms like since the beginning of the COVID-19. But lately, I don't know, it might be, the flu or allergy. I wasn't able to, get out of my bed and then go out, and I decided to take the test. I went to one of the testing locations. It took me less than 2 hours to get my results. It was faster than I expected. The procedure is, I don't recommend to put that thing in your nose. It is horrible. Like you can see
I've
that.
heard that.
Yeah, you have to stick it up in your nose, like right here, where your sunglasses are. And then they take a sample. In 2 hours, they give you your results. So it was negative. Maybe that's why I'm in the mood, because I was worried. Like taking into consideration that my wife is pregnant and she might get the COVID-19. That's a bad scenario. But you never know. So if something happens, if I get sick, or if I have the baby coming in 2 weeks, we can still adjust the schedule, but we have a flexible schedule. We are already ahead of our schedule. And I can even make up class. So let's say we missed the class, and I can have makeup class. You can join my lecture either on the weekend or in the nighttime if you want to, or you can watch the video when you have your time on YouTube. So I believe everything is clear, and I will either recommend for you to go over everything that we have discussed on Moodle before the midterm exam. So you have all the files that is on Moodle, has to be on your laptop. So when you look at the question, you can search on the PDFs, you can look at the equations, etc., etc. And I'm gonna give you guys one day, 24 hours to finish your exam. Okay? That's what you're gonna have.
Sounds good.
So I save this, and I'm gonna upload this one on Moodle. So while I'm doing this, I'm gonna be answering other questions if there are questions. If not, you're more than welcome to leave.
All right. Well, thank you for the class, and I hope congratulations on the kid, by the way.
Thank you, Piero.
What are you gonna name your kid?
Murat, my name.
Really? It's gonna be a little Murat Jr.
It's gonna be Murat Stefanos. So I'm Turkish and my wife is Greek. So it's gonna have Turkish and Greek name. My father-in-law, his name is Stefanos. He's Greek. We're gonna keep 50-50 Turkish and
That's cute.
Greek name. Yeah.
That's
Yeah,
awesome.
Thank you. So we just finished preparation of the room. I wasn't able to spend more time with my wife because of my schedule with school and research and the new way of teaching. It's new for everybody. Online. I'm more comfortable when I'm in the class. Well, we're getting used to it,
Well, have a good night. Thank you.
Have a good night, Andrea. Like I said, if you have questions, just give me a call rather than email.
All right.
Very easy.
All right. Thank you very much.
Have a good night.
I actually have one more question. So I did the assignment, the lab assignment, and I turned it in right before class, but I couldn't find the submit button in the Turnitin. It wasn't on there for me, so I just turned it in the quiz. Is that all right, or do you want me to email it to you and explain all that?
I have to explain all that. So you just did, what did you do?
I did the assignment, the lab assignment, but I turned it in under the Turnitin for the quiz submission instead of the virtual lab assignment submission because for some reason mine did not have the submit button.
That's okay.
Okay.
I'll take care of it.
I can email you and remind you of that. So.
Okay, you can just email me then. So if I get confused, I always go double check with the emails. You know?
Yeah. I could do that right now. I just wanted to make sure it wasn't like a bad thing I did.
Okay. I will also change this date to October 7th.
What do you know about the Artemis program?
I don't know about the Artemis program. Oh yeah, but how come we haven't sent anybody since like
So if you haven't submitted
1972?
yet, you can submit it again.
Yeah.
Because
Thank you.
We already picked up the samples. We did everything that
Have a good night.
needs to be done to develop the research.
So I'm assuming that you guys have question. If you don't have question, I'm gonna stop this meeting. Kate, Kaden, Laura? No. Then have a good night, guys.